Welcome back, everyone, to the Foundry by Forge College. If you've been following along in our advanced Solana concepts track, you know we're right in the thick of the Understanding Sealevel execution course, and specifically, we're diving deeper into the resource management in Sealevel module. All right, let's get right into this explainer. Today, we're bringing some serious energy to a highly technical topic. We are literally decoding the engineering blueprints of Sealevel's CPU management. Here's what's on the docket for today. We'll start with a welcome to the CPU theater, then look at metering to tame the actors, isolation and prioritization, some real-world Web3 scenarios, mental models for devs, and finally, wrapping up CPU management. Let's jump in. Section 1. Welcome to the CPU theater, from account locks to spotlight time. So in our previous explainer, the Introduction to Resource Management, we looked really closely at account locking. That answered a fundamental question. Can these run together? Are they conflicting? Well, now we're shifting gears to the next big question. How much processing time do they actually get? It's kind of like this. Think of locks as the traffic lights keeping an intersection safe. CPU management, on the other hand, is the rule dictating exactly how long your transaction gets to drive before it absolutely has to pull over and let someone else pass. To really wrap our heads around this, let's unpack a pretty fun central metaphor. Imagine the Sealevel runtime as a massive, multi-stage theater. Step 1, your transactions? Those are the performances. Step 2, CPU time is the spotlight. Step 3, the accounts your transaction needs to read or write are the props. And step 4, the Sealevel scheduler is the house manager. And let me tell you, they are incredibly strict. Look, if two performances need the exact same prop, the manager just won't let them on stage at the same time. One has to wait backstage. But here is the real kicker. Even if you have all your props ready to go, how long do you actually get to stay in that spotlight? Section 2. Metering. Taming the actors. Enforcing the rules of the stage. Okay, the most crucial point here is that Sealevel treats CPU as a strictly metered, totally fungible resource. Enter the compute budget. This is a strict per-transaction limit on instruction execution. Going back to our theater, this is the absolute time limit for a single performance. See, every single instruction a BPF program executes costs a specific accounting unit, and the runtime is meticulously counting these up behind the scenes. If your transaction, your actor, hits its budget and refuses to leave the stage, boom, the runtime explicitly halts the execution. It essentially pulls the trapdoor right out from under them. It returns an error saying the compute budget was exceeded. This is an absolutely crucial safety valve against buggy, diva actors trying to hog the stage and ruin the node's ability to process other parallel work. But wait, there's another layer to this whole thing, the per-slot compute cap. This is a validator level limit. If the per-transaction budget is the limit for one single performance, you can think of the per-slot cap as the theater's overall operating hours for the entire night. Even if every individual performance is perfectly under budget, the total drawn compute credits across all the parallel threads cannot exceed the physical CPU available to the validator during that slot window. Both of these limits are absolutely essential. They give the scheduler deterministic signals to enforce fairness and, keep the network alive and processing. Moving right along to Section 3, isolation and prioritization, VIP passes and backstage waiting. Let's dive into how this actually works across parallel worker threads. The validator's worker pool has to provide isolation, right? Otherwise, one thread's incredibly heavy compute load could totally starve the others. First up, account locks isolate workloads. If transactions have disjoint accounts, meaning they use completely different props, they can run concurrently on totally separate stages, no problem. Second, workers will cooperatively yield if a budget is exhausted. And third, global synchronization is minimized. Sealevel avoids a massive, performance-killing global pause by handling all of this super elegantly right within the worker pool. Now, what about prioritization? If some transactions are way more urgent, they can signal for higher priority. But please remember this critical rule. Priority by scheduling preference, not infinite CPU. I really can't overstate how important that distinction is. Buying a VIP priority pass definitely gets your transaction on stage faster. It bumps you right up the line when you're competing for scarce CPU. But it absolutely does not give you a longer performance slot. You still have to respect those strict compute budget caps we just talked about. So you get on stage sooner, for sure, but you don't get to stay on stage forever. Section 4, Real-World Web3 Scenarios. Case studies on the runtime stage. Let's look at 3 real-world scenarios to really ground this. First up, a high-frequency DEX. Its compute profile, moderate to high.
The conflict pattern is low if order books are partitioned, but high if they share a common escrow account. The scheduling outcome here is high parallel throughput, but it gets kind of slowed down by those heavy matching computations. Next, let's look at a batched faucet. Low compute per transaction, very low conflict if the transfers touch disjoint accounts. Outcome? Massive parallel throughput. Huge! However, if the faucet accidentally bundles operations targeting the exact same hot account, well, everything serializes and your throughput completely plummets. Finally, Oracle updates. Very low compute per update, but extremely high conflict because everyone is trying to write to a single aggregator account. The outcome? Serialized updates. This perfectly demonstrates how your conflict patterns and compute profiles directly dictate your fate in the Sealevel scheduler.
On to Section 5, Mental Models for Devs, Engineering for Parallel Throughput. All of this naturally leads us to a pretty vital question for anyone building on this network. How do we actually predict our app's behavior under load? In a lot of our other Forge College courses, we heavily emphasize the importance of mental models. Why? Because having the right framework completely changes how you architect and debug your code. It's a total game changer. To answer that question, we have two complementary ways to evaluate resource consumption. First, we have the theater model. This is what you're going to use when you want to focus on ordering, preemption, and account conflicts. Will two transactions need the same props? If yes, one waits backstage. Simple. Second, we have the credit balance model. Imagine the validator's CPU as a massive credit balance per slot, and every single transaction draws from it. You use this model to focus on overall throughput, slot caps, and worst-case usage. Like, if 1,000 concurrent transactions each use X amount of credits, can the validator actually support that before the slot finishes? Being able to seamlessly switch between these two models gives you a complete 360-degree view of your application's performance boundaries. Finally, Section 6, Wrapping Up CPU Management. Final heuristics and next steps. Let's synthesize all this into some actionable heuristics you can use right away to maximize your depths. Number 1, keep critical latency operations small and disjoint so they get scheduled rapidly. 2, split or shard hot accounts. You really want to avoid that dreaded serialization we saw with the Oracle example. 3, if you absolutely have heavy computation, break that work up into smaller atomic steps so you don't exhaust your per-transaction compute budget. And 4, use priority signaling thoughtfully. Remember, it buys you the stage earlier, not a longer performance. Ultimately, you have to remember that Sealevel is fundamentally optimizing for many small, disjoint tasks, rather than big, monolithic, sequential ones. I want to leave you with this really powerful design philosophy. Design for low conflict first, then optimize compute complexity second. Always, always prioritize splitting your state. If you do that, Sealevel's parallel scheduler will reward you with incredible throughput. But ask yourself this. If you've perfectly optimized your CPU usage, what happens if your memory state is bloated? Are you just shifting your bottleneck from the processor over to the RAM? Well, in our next explainer, we're going to dive into memory efficiency techniques in Sealevel to answer exactly that and complete your optimization toolkit. Thank you so much for joining me for this explainer. To continue your journey in mastering Web3 and to explore more deep dives exactly like this one, make sure to visit forge.college. See you in the next one.